I thought today we could have a chat about randomized testing, also known as fuzzing, which is a really effective technique for finding bugs in software. Where fuzzing began is actually slightly disputed. It's one of those techniques which is pretty obvious. You have some software, and then when we design software as programmers, we normally think about what the software is supposed to do, how people should use it, and maybe the kind of mistakes they would naturally make when using it. We don't often think about absolutely crazy ways to use the software. So for example, if you had a word processing application, you would think about the layout, you'd think about the features it should support, and you might think about things like the user trying to open a file that doesn't exist. But you might not necessarily consider cases where they make a document where they paste in all sorts of crazy content, or you might not think about them trying to open, say, a video file with the word processor and what would happen there. So often software goes wrong because of unexpected inputs that the programmer didn't think about, and randomized testing is a great way of finding those kinds of unexpected inputs. Fuzzing has become more and more important in the internet age because if you think about systems like web browser, Chrome, Safari, Firefox, used by billions of users around the world, these are completely open systems. With a phishing attack where you trick someone to click on some web page, takes them to a random web page, a malicious web page, that web page can have arbitrary content. So the web browser needs to be able to be robust against completely arbitrary HTML. It doesn't necessarily need to render anything meaningful for the HTML, but it must not be the case that random HTML or JavaScript can expose a vulnerability in the web browser. And with recent news about things like Claude Mythos, the large language model that there's quite some concern about when people talk about vulnerabilities, it's things like the kind of inputs that could cause an open system like a web browser to not just misbehave, but actually provide the entry point for, say, a remote execution attack. That's the kind of thing people are concerned about. And fuzzing is a really good way to defend against those kinds of problems because by testing a system with random inputs, you may be able to accidentally stumble upon some of these backdoors. There are really two extremes of what people want to do with fuzzing. On one extreme, you want to randomly test software using garbled, malicious inputs that should not really be fed to that software with the aim of trying to find vulnerabilities in the software. Then at the other end of the spectrum, you might want to test software with very highly crafted, well-formed inputs, but super complicated inputs, and actually try to see whether the software did the right thing on those kinds of inputs. And researchers are interested in advanced techniques at both ends of the spectrum. So perhaps I'll start by talking about the ways you might use fuzzing, which is also known as randomized testing, for testing complicated systems where you want to check they really did the right thing. So a really nice example here is compilers. Compilers like GCC or Clang for C or Java-C for Java. And there are many, many programming languages with multiple compilers often per language. And a compiler, like any program, can crash if you give it some kind of expected or unexpected input. There may be a bug that simply causes the compiler to crash. But with a compiler, there's a worse kind of bug, which is known as a miscompilation, which is where you give the compiler some source code, and the compiler uncomplainingly turns that into binary. It turns it into executable object code, and it doesn't indicate that anything has gone wrong in the process. However, the translation from the source code into the executable binary code has not represented the meaning of the program. The semantics of the source program haven't been obeyed. So as an unrealistically simple example, if the program said x plus y and the compiler translated that into a multiply instruction that would multiply x by y, that would be a miscompilation. Now, we hope that a compiler never made such a drastic error as that, but compilers do really sophisticated optimizations when translating code from source code into assembly, and these optimizations can have edge cases the compiler developer didn't think about, and they may not work in all settings. They should, but they may not. So a really interesting line of work using fuzzing to test compilers involves creating a fuzzer, a random generator that randomly generates programs in a given programming language that should actually be well-formed programs. They wouldn't do anything meaningful. They would just use the features of the language in all kinds of weird and wonderful ways. They're not to produce any desired effect, but so that when you would run one of these randomly generated programs, it would produce some output. Perhaps it would just print an integer. What the integer would be would entirely depend on the random structure of the program, but the challenge is to generate programs that when you would run them, you would get a deterministic integer result. then what you can do is you can say, if you've got two compilers under test, for argument's sake, I'm going to say GCC, the GNU C compiler, and Clang, another very well-known open source C and C++ compiler. If you have got your fuzzer, which is a piece of software that's going to generate programs, then the fuzzer is going to generate some program. So what's in this program is going to be randomly determined by the fuzzer. However, the program is going to be an entirely deterministic program. We can give this program to GCC, we can give it to Clang, and they will compile this program into executables. Let me call them 1.exe and 2.exe. Now, if we run these executables on the same input, so let's say we give them some input I, and we give them both the same input I, and this program gives us an output O1, and this program gives us an output O2, then these outputs should be equal. The fuzzer has generated one program, we've given that program to both compilers, we've compiled the program to get two executables. These executables might be really different from one another because the compilers might have made different decisions on how to optimize the code. So they will have different ways of generating a binary representation of the source code. But those binary representations should encode the same thing. They should both encode the semantics of this program. If we then run them on the same input, we should expect to get the same output. And if we don't, then that indicates that something's gone wrong in the compilation process. There must be a bug in one or other of these compilers. Now, there are some important caveats here for your viewers who know about C and C++. These languages are full of undefined behavior. And if this program was subject to undefined behavior, it might be that actually these executables could be expected to produce different results because of the undefined behavior. So the real challenge is that we must make sure there is no undefined behavior, no UB in this program.
What's an example of undefined behavior then?
In C, an example of undefined behavior is dividing by 0. Okay. So often that will cause the program to crash, but actually that's not guaranteed. The language doesn't say that a division by 0 causes the program to crash. It's actually undefined. Oh. Another example is reading from an array out of bounds, so an array overflow or an array underflow. And there are actually a huge number of examples of undefined behavior in the language. That's an example of randomized testing applied in the domain of compilers. And there is a tool that originated from the University of Utah called CSmith, because it's a smith of C programs. And CSmith is the fuzzer that creates these randomized C programs. And the key innovation in that CSmith project is exactly producing programs that don't have this undefined behavior. Okay. So this is an example of fuzzing to try to find deep functional bugs in a complicated piece of software, a compiler. It's not trying to find security vulnerabilities where when you feed the compiler gibberish, the compiler crashes with an exploitable vulnerability. That's not the purpose of this fuzzing. It's really to try to find deep problems where the compiler is actually wrongly optimizing a program. There's a genuine bug in the program.
Okay. And do you get to the point where you can categorically prove a problem with it, or is it a bit like any science where you might test it 1,000 times and they all seem fine, and so therefore you still can't prove that it's fine because the 1,001st one might be a...
That's right. So generally software testing of any kind is about showing the presence of bugs, not proving the absence of bugs. So you can't use testing to show that software is correct. You can only use it to show the software is not correct, but the process of repeatedly showing that the software is not correct, fixing it, and then it becoming harder and harder to find bugs in the software gives evidence the software is becoming more and more reliable. Now, a very difficult problem that some academics are interested in, I think it's interesting, but it's not something I worry about, is how do you know that you found all the bugs? I guess my practical perspective from my time working in companies is that you never do. You never find all the bugs unless you're working in high assurance safety critical software where you're really using formal verification to prove that a software is correct. If you are not working in that domain, then all software has bugs. Yeah. And then a very relevant question is, which bugs do you care about? So do you care about all these bugs fuzzers can find? So fuzzers sometimes find problems that are bugs, but whether anyone would ever fall foul of one of these bugs is up for question, and that in itself is quite an interesting issue.
The thing about any of this is that obviously with the sort of systems we use now, I mean, I'm going to call to mind that XKCD.
The Nebraska.
The Nebraska one with the tiny leg.
Yeah.
And, you can look at what you're looking at, but it could be sitting on top of so many other possible kind of frameworks and platforms.
That's right. So these techniques need to be deployed with a context in mind. So I think, this work on these Unix utilities, the idea there is really that these utilities, although they're some of them are very simple tools, huge numbers of people are using them, and you don't really know what they're using them for, all kinds of things. So there's a really good case for trying to make those super reliable. Compilers, we know that many companies depend on compilers like GCC and Clang. They're some of the best examples of open source projects we have. So there's a very strong argument for making them be as bug-free as possible. That said, does it really matter if GCC falls over when you give it a file full of non-printable characters? If it doesn't compile that, if it just crashes with a fatal error, as opposed to saying, syntax error, does that really matter? Is that a bug that actually matters? I would argue no. So, even something as critical as GCC, not every bug in GCC is important. And I want to talk about coverage-guided fuzzing, which was popularized by a tool called AFL, American Fuzzy Lop, which was from a developer at Google some time ago that has really then paved the way for a huge amount of practical work and also research into fuzzing. Let's say we've got a system that we're trying to test, SUT, system under test. If we think about the functionality of the system being a bit like a maze, there are all sorts of places that you could get into in this system, then if you're firing some kind of random input at this system, some random bytes, then it may be that this gets into some parts of the software, and then you fire another input and it gets into some other part of the system, and then another input gets into a slightly different part of the system. But it might be that actually for an input to get any further into the system, it might have to have certain features. For example, it might be that you've got to be giving some valid command line arguments to a Linux utility to unlock a lot of its behavior. So many utilities, when you run them, you provide a lot of arguments on the command line, and if you provide a certain argument, then the input will be treated in a particular way. So there may be whole portions of the system you're never going to reach unless you provide that correct argument. So this approach, while it might find some pathological cases where a system crashes, it's unlikely to find inputs that drive the system into really deep and interesting states. A technique that overcomes that problem is known as coverage-guided fuzzing, and it was popularized by a tool called AFL, American Fuzzy Lop, which was developed by a Google engineer some time ago and has led to lots of follow-on practical work in industry and also lots of academic research work and various other fuzzers like Google's libfuzzer, for example, which is an AFL-style fuzzer. Once again, if we think about our system under test being maze-like, the idea of coverage-guided fuzzing is that we have got a corpus of inputs that are being used during the testing process. Initially, this corpus might have some example real-world inputs for the system. So for example, if the system was a PDF engine, we might have a selection of example PDFs that already get some coverage of this system. And the idea is to try to find inputs that go deeper into this system, get further into the maze, with the hope of finding bugs. So let's suppose that there is a bug lurking somewhere in this maze. The idea is we don't know where this bug is, but by exploring the maze, we're hoping we will find one or more of these bugs that can then be fixed to make the system more reliable. So the idea of coverage-guided fuzzing is, let's say this corpus contains a number of inputs, but maybe initially it contains some input A. And here I don't mean literally the character A, I'm just calling A the input. A might be a PDF, for example. Then what the fuzzer is going to do is it's going to pull out this input A from the corpus, and then it is going to randomly mutate A to give a mutated input. Let's call it A prime. And the mutations that are done to go from an input A to A prime are randomly applied, and they can include things like flipping a bit, or replacing a sequence of bytes with another sequence of bytes, or deleting some bytes from the input, or taking two inputs and splicing them together, for example. So now this A prime is going to be fed to the system under test. And A prime will get some coverage of the system, which we can think about as making some progress through this maze. So if this progress through the maze that A prime made means that we get to bits of the maze, i.e. bits of the software that have never been reached before during fuzzing, then this input A prime is deemed to be an interesting input that might be useful for further consideration. So it is put back into the corpus. Let's call it A prime. I'm being a bit inconsistent with my colors here.
That's okay. We got it.
Okay. So now let's suppose that there was another input in this corpus. Let's call it B. And the fuzzer pulled B out and applied a mutation to it to get B prime. And then B prime is fed to the SUT, the system under test. Let's say that B prime actually just retreads some of the path that A prime took. So it achieves some of the coverage, maybe all of the coverage that A prime achieved, but no more coverage. Then B prime is not deemed to be interesting. It didn't get any further. We didn't see anything new from B prime, so it's not going to be put back into the corpus for further mutation. But then let's say that A prime is picked out again by the fuzzer and mutated into a form A prime prime, say. And when we give this to the fuzzer, it actually gets a bit further into the system under test. Then that's great. A prime prime is getting places that we've never seen before. It's interesting, and it gets put back into the corpus to be considered in the future. And the idea is to do this process at speed, ideally thousands or tens of thousands of times per second, and mutate inputs guided by coverage. So new coverage is interesting, to make them more and more sophisticated to get deeper into the system. And it might be, if we're lucky, perhaps the third time we mutate this input. So we go from A prime prime, let's call it A prime prime prime. When we give this to the system, it might be that now this gets even more coverage and bang, hits this bug. The system crashes. That's excellent. We found an input, A prime prime, that causes the system to crash. And now a developer can go and investigate what's wrong and fix the bug. So that's coverage-guided fuzzing. And we can see this as an example of an evolutionary algorithm. We've got a population, the corpus, and we've got the notion of randomly mutating inputs, so random mutations in the population. I mentioned also that one of the mutations involves taking multiple inputs and splicing them together, mating inputs to form new inputs. And we've got a fitness function, so these inputs only survive, they only get put back in the corpus if they are fit, which means they get new coverage. So this fuzzing approach can be seen as evolving a corpus of inputs into richer and richer inputs that get further into the system under test to trigger bugs. Let's say that we've got some utility that takes command line options, the example dash dash only. The probability of having an input that's got a dash at the beginning is quite high. There aren't that many characters, and after many iterations, we're probably going to find a dash, and there'll be code that processes command line inputs, and that code will get a bit deeper if we do provide a dash. But then if the next character isn't a dash, then we won't have dash dash, which is the beginning of an input. But because we found one dash, that will go back into the corpus. And in the future, it's fairly likely that a mutation will add a second dash to this. And then in the future, it's quite likely we'll start to get the character O, for example, and then N, etc. So after many, many, many iterations, but not an astronomical number of iterations of this process, the fuzzer will implicitly start to discover the expected format of inputs and get deeper into the system.
Now, if I flip this around, and if all of the second thread was executed before all of the first thread, I will have the symmetric situation where A is 1 and B is 0. The question is, could I also have observe A is 0 and B is 0?